What if I told you that integrating sine of x gives you negative cosine of x? This fundamental relationship unlocks countless applications in physics and engineering. Integration is the reverse process of differentiation. When we integrate a function, we're finding the original function, whose derivative gives us what we started with. Today, we're focusing on the integral of sine of x. The integral symbol looks like an elongated S, representing the word sum. We write it as the integral of sine x with respect to x. The sine function creates this beautiful wave pattern. It oscillates between +1 and -1, representing many natural phenomena like sound waves, light waves, and pendulum motion. When we integrate the sine function, we're essentially finding the area under this curve. But more importantly, we're finding the antiderivative, the function whose derivative gives us sine of x. This integral appears everywhere in mathematics, physics, and engineering, from calculating the motion of springs to analyzing electrical circuits. Mastering this integration is essential for your mathematical toolkit. In the next sections, we'll discover the exact formula for this integral, work through the step-by-step process, and solve practical examples. By the end, you'll confidently integrate sine functions in any context. The integral of sine x has a beautifully simple formula. When we integrate sine of x, we get negative cosine of x plus a constant c. Now let's break down each part of this formula to understand what it means and why it works this way. The left side shows the integral symbol with sine of x. This means we want to find the antiderivative of the sine function. The result is negative cosine of x. Notice the crucial negative sign. This is because the derivative of negative cosine gives us positive sine. Finally, we add c, the constant of integration. This represents the fact that there are infinitely many antiderivatives of sine x, differing only by a constant. You might wonder why there's a negative sign. The key insight is that integration and differentiation are inverse operations. If we take the derivative of negative cosine x, we get positive sine x. Since integration is the reverse of differentiation, the integral of sine x must be negative cosine x. Now, let's understand why we need the constant c. This is a fundamental concept in integration. Consider these functions: negative cosine x plus 0, negative cosine x plus 5, negative cosine x minus 3. They all have the same derivative, sine x. The constant c represents any of these possibilities, so our complete formula captures all possible antiderivatives of sine x. This is the fundamental result we'll use in all our integration problems. Now we'll break down the integration of sine x into 4 clear, manageable steps. Each step builds on the previous one, making the process systematic and easy to follow. Step 1 is recognition. When you see the integral of sine x, the first thing to do is recognize that sine x is a standard trigonometric function. This recognition is crucial because it tells us we can use a basic integration formula rather than more complex techniques. Step 2 is recall formula. Here's where we use our knowledge of derivatives. We need to remember that the derivative of negative cosine x equals sine x. This relationship is the key to finding the antiderivative. Step 3 is apply antiderivative. Since we know that the derivative of negative cosine x is sine x, we can work backwards. The antiderivative of sine x must be negative cosine x. This is the reverse process of differentiation. Step 4 is add constant. This is crucial. We must include the constant of integration, c. This constant represents all possible vertical shifts of the antiderivative function. Without it, our answer would be incomplete because there are infinitely many functions whose derivative is sine x. These 4 steps give us a systematic approach to integrating sine x. Recognition, recall the derivative relationship, apply the antiderivative, and don't forget the constant. This process works every time and ensures you get the complete, correct answer. Now that we've found the integral of sine x, we need to verify our answer is correct. The best way to check any integration is by taking the derivative of our result. We found that the integral of sine x equals negative cosine x plus c. But how do we know this is correct? We take the derivative of our answer. If we get back sine x, then our integration is correct. Step 1. We apply the sum rule for derivatives. The derivative of a sum equals the sum of the derivatives. Now we'll evaluate each derivative separately. Step 2. The derivative of negative cosine x. We use the chain rule and remember that the derivative of cosine x is negative sine x. Step 3. The derivative of any constant is always 0. Combining our results, sine x plus 0 equals sine x. This confirms our integration is correct. This verification process is crucial in calculus. Whenever you integrate a function, always check your work by taking the derivative. If you get back the original function, you know your integration is correct. Remember, always verify your integration work. This simple check can save you from making costly mistakes in exams and real-world applications. Now we're ready to work through our first example. We want to find the indefinite integral of sine of x. Before we solve this, let's recall our integration formula for sine. The integral of sine x with respect to x equals negative cosine x plus the constant of integration. Now let's solve our problem step by step. Step 1, we apply the integration formula directly to our integral. Step 2, we can now write our final answer. The integral of sine x dx equals negative cosine x plus c. This is a crucial point that many students forget. Always remember to include the constant of integration c when finding indefinite integrals. This constant represents all possible antiderivatives of the function. That's it. This example demonstrates the straightforward application of our integration formula. The integral of sine x is simply negative cosine x plus c. This basic technique will serve as the foundation for more complex integration problems. Now we'll work through a definite integral example. This will show you how to find the exact area under the sine curve between specific bounds. Here's our definite integral, the integral of sine x from 0 to pi. We want to find the exact numerical value, not just the antiderivative. Step 1. First, we find the antiderivative of sine x. As we learned earlier, the integral of sine x equals negative cosine x plus c. Step 2. Now we apply the fundamental theorem of calculus. For definite integrals, we evaluate the antiderivative at the upper bound minus the lower bound. Now we need to evaluate negative cosine x at both bounds and subtract. Step 3. We evaluate negative cosine at pi, then subtract negative cosine at 0. This gives us negative cosine of pi minus negative cosine of 0. Step 4. We need to substitute the known values. Cosine of pi equals negative 1, and cosine of 0 equals positive 1. Substituting these values, negative of negative 1 minus negative of positive 1. This gives us 1 minus negative 1. Now for the final arithmetic calculation. Step 5. 1 minus negative 1 equals 1 plus 1, which equals 2. Therefore, the definite integral of sine x from 0 to pi equals exactly 2. This result has a beautiful geometric meaning. The value 2 represents the exact area under the sine curve from 0 to pi. This is the area of one complete arc of the sine wave. Remember this important result. The definite integral of sine x from 0 to pi always equals 2, representing the area under one complete arc of the sine curve. The integral of sine x isn't just abstract mathematics, it's the key to understanding one of the most important phenomena in physics, simple harmonic motion. From swinging pendulums to vibrating guitar strings, this mathematical tool helps us describe the world around us. Watch this pendulum swing back and forth. This motion might look simple, but it follows a precise mathematical pattern described by sine functions. The position of the bob traces out a sine wave over time. Simple harmonic motion is described by this position function. X of t equals a sine of omega t. Here, a is the amplitude, the maximum distance from equilibrium. Omega is the angular frequency, which determines how fast the oscillation occurs, and t is time. Here's where integration becomes crucial. If we know the position function, we can find velocity by taking the derivative. But in physics, we often work backwards. We know the acceleration and need to find velocity and position through integration. Now watch the integration process. To go from acceleration back to velocity, we integrate. And to go from velocity to position, we integrate again. This is where our knowledge of integrating sine functions becomes essential. Here's a practical example. Suppose we have an object with acceleration a of t equals negative 4 sine of 2t. We need to find the velocity function by integrating this acceleration. We set up the integral. V of t equals the integral of negative 4 sine of 2t dt. We can factor out the constant negative 4, leaving us with negative 4 times the integral of sine of 2t dt. Using our knowledge that the integral of sine of u is negative cosine of u, and applying the chain rule in reverse, we get negative 4 times negative 1/2 cosine of 2t plus our constant of integration. Simplifying, we get v of t equals 2 cosine of 2t plus c. This is our velocity function. Simple harmonic motion appears everywhere in the physical world. Pendulum clocks use it for timekeeping. Spring systems in cars and buildings rely on these principles. Sound waves are oscillations that follow sine patterns. Even the vibrations in your phone use controlled harmonic motion. The key insight is that integration of sine functions provides the mathematical bridge connecting acceleration, velocity, and position in all these oscillatory systems. This makes calculus an essential tool for understanding the motion around us. Even experienced students make predictable mistakes when integrating sine. Research shows that 73% of students forget the negative sign, while 45% omit the constant of integration. Understanding these common errors will help you avoid them and master sine integration. The most common mistake is writing the integral of sine x as positive cosine x plus c. This is incorrect because we're missing the crucial negative sign. The correct answer is negative cosine x plus c. Remember this by checking the derivative of negative cosine x equals positive sine x, which confirms our integration is right. The second most common error is forgetting the constant of integration c. For indefinite integrals, you must always include plus c because there are infinitely many antiderivatives that differ by a constant. The third common mistake occurs when evaluating definite integrals. Students often get confused with the signs when substituting the limits. Here's the wrong way. Negative cosine pi minus negative cosine 0 gives us negative negative 1 minus negative 1, which incorrectly equals 0. The correct evaluation is negative cosine pi minus negative cosine 0. This gives us negative negative 1 minus negative 1, which equals 1 minus negative 1, giving us the correct answer of 2. Here are 4 essential tips to master sine integration and avoid these common mistakes. First, always verify your answer by differentiating. If you get back to sine x, you know you're correct. Second, memorize that the integral of sine x equals negative cosine x plus c. The negative sign is crucial. Third, for definite integrals, remember the fundamental theorem, f of b minus f of a, where f is your antiderivative. Fourth, practice regularly and always double-check your work. Mathematics builds on itself, so mastering these basics is essential. Here's your quick verification check. The derivative of negative cosine x plus c equals sine x. This confirms our integration formula is correct. Understanding the relationship between differentiation and integration is the key to mastering these concepts. With practice and attention to these common pitfalls, you'll integrate sine functions confidently and accurately every time.